Good morning, everyone. Thank you for joining us before you head out into the woods this morning. My name is Colleen Tyler. Today's webinar is part of the Managing Our Changing Forest webinar series. This series is an initiative of UVM Extension, UVM's forestry program, and the Vermont Department of Forest, Parks, and Recreation. To find out more about the webinar series or listen to archive webinars, go to www.ourvermontwoods.org/forestry webinars. While you're there, feel free to sign up for our new e-announcements about upcoming webinars. Before we get started, I'd like to go over a few logistics. As participants, your microphones will be muted during the webinar. However, we do want to hear from you. Please use the question box in your GoToWebinar side panel to type in any questions you have for the presenter. Questions will be addressed in the order in which they came in. Lastly, this webinar is approved for one SAF Continuing Forestry Education credit, as well as one Vermont Forester Licensing credit. At the end of the presentation, you will be asked to follow a link to a very short survey. This survey will only take 5 minutes, and the feedback helps us to improve our webinars. It also offers a place for you to request the credits. Certificates will be emailed out by the beginning of next week. This webinar is being recorded and will be archived as a YouTube video on the webinar series webpage. With that, we'll get started. Today's webinar presentation is titled Tree Biomechanics 101. Our presenter today is Amanda Bunce. Amanda received her undergraduate degree from Central CT State University. She earned a master's in natural resources from University of Connecticut. For the past 3 years, she had worked on urban forestry initiative called Stormwise at UCONN, as well as working as a forestry research technician. She plans to start as a PhD program next fall. She worked as a gardener, a logger, and an outdoor educator before getting into postgraduate work in forestry at UConn. She still does some lumberjacking on the side, volunteers with a dog rescue, and has a small sugaring operation going this time of year in Ashford, Connecticut. So I guess I will pass it to you, Amanda.
Okay, thanks, Colleen. So Tree Biomechanics 101. So for the last few years, I've been working at UConn, and I've had an opportunity to learn all about tree biomechanics, and that's what I am about to share with you guys. We often just call the subject wind in trees. It's all about how trees react to wind and their dynamic properties. Dynamic properties describe movement. So that's what we're going to get into today. Okay. All right, so the biomechanics of trees is the study of tree structure and movement. And we're going to cover tree sway, which is movement. It is the immediate reaction to the force of the wind. We're going to look at properties which describe moving the wind energy or avoiding it, so how trees handle that wind energy. Then we're going to talk about the long-term developmental responses to wind. That would be morphogenesis. We'll get more into that fun word later. And we're going to talk about the application of some of these principles in arboriculture and forestry. And I'm going to talk to you a little bit about the research project that I do here at UConn. All right, so with that, let's just jump right into tree sway. So tree sway, it is the immediate reaction of trees to the force of the wind. And it is a mechanism dissipating the energy that's forced on the trees by the wind. So wind isn't constantly pushing on a tree. It's more like a trigger. It sets the tree in motion. And this motion isn't a back and forth motion, but trees actually move in circles. Often we describe the motion as two-dimensional, but it's not. It's a periodic circular motion that these trees are waving about in the wind. So that said, break this down into a two-dimensional graph. So any periodic motion can be graphed like this, like a signal, a sinusoidal signal specifically, and it can be described mathematically by its properties, frequency and amplitude. Frequency is going to be how fast it makes these sways or these periodic motions, and then amplitude is going to be how far the tree sways, so how far it gets from its resting place, or the distance of the sway, however you want to look at it. We usually measure frequency in hertz, that's somethings per second, and we measure amplitude in a distance measurement, so I use meters because science. So we can also talk about decay, which is a loss of amplitude as your signal moves forward in time. So you can see there's bigger amplitudes at the beginning, and we're getting smaller and smaller as you go through time. The decay rate is how fast you're losing amplitude over time. All right. So sway is risky behavior. We can't sway forever, and we don't want to go too far. And by we, I mean a tree. If a tree sways too far, it'll break or it'll overturn. It'll pull up its roots and fall over. So this is called achieving an amplitude greater than your elastic capacity. As long as a tree is not moving too far, it's elastic enough that it'll come right back up to where it was before. But if it goes too far, we break or we overturn. So before that happens, what you need to do is lose the kinetic energy, the energy from the wind that set you in motion, and that's keeping the tree swaying. So we need to lose that energy. So we're going to talk about motion damping. Damping is energy lost. It's energy that's given off as heat from friction. And this friction is friction with other trees, so crown clashing. It's friction with the air, which we call aerodynamic damping or drag, or friction within the tree itself. So just its cells rubbing together as you expend energy trying to bend the tree. So the proportions to which the energy is lost was sort of nailed down in forest trees by a gentleman named Milne in the 90s. 50% of energy is lost to crown clashing, so friction with other trees, 40% to aerodynamic or drag, and 10% to the internal damping. So obviously this is going to be different for open grown trees because they don't have other trees to hit against. They can't pass the energy around from tree to tree. So these clicker balls are passing this kinetic energy from one to the other, and they keep moving. Obviously, open grown trees can't do that. They have to rely entirely on friction with the air and friction within themselves. Aspens are kind of specialized to utilize these types of friction damping. They have the flattened petioles on the leaves, and they're really great for constant bending. It allows them to vigorously just flap in the wind and lose a bunch of energy by bending, which is that internal damping, and also to drag because they're flapping in the wind. The rounded petioles of other species don't bend quite as easily. So this is why quaking aspens quake. They're constantly moving in the wind, constantly getting rid of that energy at the level of the leaf. So the energy doesn't travel down to the trunk and bend or break the tree. All right. So one more damping mechanism that Milne wasn't really aware of in the 90s is resonant damping. So this is going to be a little bit tricky. Each tree part has its own frequency. They're like a bunch of tuning forks. So the trunk, I labeled it F3 here, it has a specific frequency, and it's going to be the lowest frequency just because it's the biggest part of the tree and it's moving the slowest. The larger branches, higher order branches, are going to have higher and higher frequencies as you go up the order of branches. The smallest ones are going to move the fastest. They're basically vibrating instead of swaying. Okay, so each tree part has its own frequency, and energy is lost as a part sort of sets a different part in motion. So as a leaf starts moving in the wind and it sets a small branch in motion, and then a branch sets the trunk in motion, energy is lost as the motion energy passes to each part. So going forward, when we talk about the frequency of a tree, I just want you to know we're referring to the fundamental vibrational frequency, which is the frequency of the trunk. So even though all these tree parts have all these different frequencies, when I say the frequency of a tree, I'm referring to the frequency of its trunk. Okay, moving on from motion damping. If motion damping is sort of handling the energy and dissipating it somehow, streamlining is avoiding the energy. So you can do it instead of dissipating or in addition to dissipating the energy, but the tree is going to avoid the energy in the first place. And there are a couple ways to avoid the energy. All of them are called streamlining. This first one that's illustrated here is to develop sort of a sail consistent with prevailing winds. This is one of my favorite pictures because you can see two different species of conifer in here, and the one on the right actually developed that streamlining thing. It's got more branches on the right-hand side, so you can kind of see the direction the prevailing wind is going, and it caused the tree to develop more branches on one side where they wouldn't be in the wind so much. The other tree is a species that just doesn't streamline like that, so it stayed consistently shaped no matter what the prevailing wind was. So this is a species-specific kind of thing. Streamlining can also include developing smaller leaves. That'll give you less of a sail. Shedding branches. If you lose branches, you won't be handling so much wind. And reconfiguration for aerodynamics in higher winds. This is an illustration of what I'm talking about there. These are some leaves that reconfigure in high winds. So the tulip tree leaf rolls up, allowing the wind to sort of sail over it without actually catching the wind. And the black walnut, all its little leaflets sort of come together so the wind can fly on by without really grabbing all of them. So that is reconfiguration in high winds, which is a type of streamlining. Okay, I want to stop here really quick and see if there are any questions. I talked about sway, which is movement triggered by the wind. Then we talked about damping, which is the loss of energy by friction. And then streamlining, which is avoiding that energy altogether. Does anyone have any questions on that so far?
It doesn't look like anyone has any questions yet, Amanda.
Okay, sounds good. I know this is complicated stuff, and you're probably going to say this in the end, but anyone should feel free to email me if you wind up with any questions about it later. All right, so moving on. So remember how we don't want to achieve a sway amplitude that is greater than our elastic capacity, or we break. There's another factor at play here. It is called resonance. Resonance is a mechanistic phenomenon that can dangerously increase amplitude. So resonance is the reinforcement or the prolongation of a vibration by the synchronous vibration of a neighboring object. So that means that trees can resonate with the wind. They sync their vibrations. If the tree has a certain frequency and the wind is blowing at the same frequency, remember how I said earlier, the wind isn't a constant force. It's more like a pulse pushing on the tree. So if that pulse has the same frequency that the tree is swaying with, then you wind up increasing your amplitude exponentially. So you've all experienced this. If you have ever pushed a kid on a swing, you know how when they come back towards you, and then as they're swinging away, you give them another push. And then if you keep doing that, you keep getting your timing right, they get higher and higher and higher. So you're exponentially increasing their amplitude of swing by pushing with a synchronized frequency. So yeah, I hope that makes sense to you. So you might notice that the word resonance is familiar. We did talk about resonant damping a few slides ago, so just give me 1 minute to connect these concepts. This is an example of that exponential increase of amplitude. This is the Tacoma Narrows Bridge, which collapsed in 1940. You can see it started to sway a little bit in this first picture. In the second one, it's swaying even more. It actually starts to look like that sinusoidal signal, right? And this happens because the wind is pushing the bridge at the same frequency that the bridge wants to swing. So the amplitude of the bridge swing or sway got really extreme, and eventually the bridge collapsed. It achieved an amplitude greater than its elastic capacity. So this happens to human structures because our bridges and sometimes our skyscrapers haven't evolved with the wind. There's one more example of resonance. This is a bunch of students. Whoops, let me go back here. Yeah, so this is a bunch of students trying to be the wind. We're demonstrating resonance here. So I do this little experiment. We're trying to teach kids what resonance is. We're yanking a tree, although you can't see the tree in this video. And how far you get to yank the tree is how strong of a wind you've pulled with the force of. But you get the most distance if you can actually achieve a resonance with the tree. So every time the tree starts swaying back towards you, that's when you pull it again, and you get greater and greater amplitude out of it. So you're trying to match your frequency with the tree frequency. However, you might notice that it's pretty hard. We don't actually manage to pull that tree down. That is because trees have a defense mechanism against resonance, and it's called resonant damping. So resonant damping is a mechanism wherein the tree passes motion from one part of the tree to another, where each of the tree parts has a different frequency, right? And we mentioned that that helps to dissipate energy, but it also keeps resonance from occurring. So if you imagine the trunk is a tuning fork with its own frequency, maybe it's achieving resonance with the wind, so it's matching the frequency of the wind. But then you have all these other tree parts that are connected to it, and they're each set in motion, and they each have a different frequency, and then they're all fighting to have their own frequency and give the part that they're connected to the same frequency, and they're all messing each other up. And if this was actually a bunch of tuning forks connected, it would be like a cacophonous disaster. But for a tree, it does is just make sure that the tree can't actually achieve resonance from the wind. All these different parts are messing each other up so much that none of them can really sync up with the wind. So it prevents that exponential increase in amplitude. So just to recap, resonance is the increase in frequency when the tree frequency and the wind frequency match. And resonant damping is a decrease in frequency due to the fact that the frequency of any tree part that is touching another tree part doesn't have matching frequencies. So, okay. Does anyone have any questions on resonance? Just quick before we move on.
Still don't have any questions yet.
Okay. I'm just going to assume that I am making perfect sense. Okay. So we are going to move on. We're going to talk long-term response of trees to wind, which is called thigmomorphogenesis. It's the development of wind firm features over time. So the term thigmomorphogenesis, thigmo refers to the physical world. Morpho is how you look or what your features are, and genesis is development. So that is exactly what the term means. Thigmomorphogenesis is a growth response to mechanical stimuli. That was coined by a man named Mordecai Jeffy in the 70s. In a paper entitled Thigmomorphogenesis, the response of plant growth and development to mechanical stimulation. So these are changes in a plant over the life of the tree in response to it being physically messed with. Specifically, when we're talking about trees, we're talking about responding to the wind. The wind is the physical stimuli that is messing with the tree and causing it to develop in certain ways. And all of these responses, these changes, they're all going to involve differences in resource allocation. So that's pretty much all a tree can do. It can't get up and move in response to being, pushed around. All it can do is differently allocate where it's putting its carbon down, basically. So we're going to illustrate that a little bit here. What we have are two examples of thigmomorphogenesis. The first one on the top is an experiment by Jaffe. You can see that the plants that were not messed with at all are larger looking. The ones that were either rubbed by hand or exposed to wind are smaller looking. The stimulated plants there look smaller, but they're not actually smaller. What they did was allocate their resources differently. So they put a lot more carbon into the thickness of their stems and probably a lot more into their root structure. So they have more stability than the ones that were untreated over there. The second picture is of basil production. So we run these rubber flaps over the tops of basils on a regular basis to encourage this thigmomorphogenic response. That way we get stronger stems and they're not leggy. Basil will grow all kinds of leggy and stretched out if we just let it. So we slow it a little bit to sort of allocate some resources to stability. So we get shorter stems, the leaves are more compact together there in less space. We also get more root growth, which is better for transplanting these little basil plants later. This is an example in nature. When we're talking about trees, like I mentioned, we're talking about wind being the mechanical stimuli. These are both Jeffrey pines. They're the same type of tree, but they have experienced different wind regimes over their lives. So obviously the first one didn't have enough wind to really make it do anything special. The second one, you can see a completely different morphology develops. Specifically, it's a streamlining morphology. You can actually see the prevailing wind direction in the way that tree grew. So this is a pretty extreme example, but here are some normal southern New England trees. On the left, we've got some closed canopy forest. That's just a bunch of younger maple trees. And on the right, there's an open grown tulip tree on the UCONN campus there. So you can kind of see the differences in carbon allocation. When you're in a closed canopy forest, all your carbon as a tree has to go to height growth. You really need to develop a lot of height to get your leaves up there so that you can photosynthesize and continue to live. You only develop as much stability as you need. You have your neighbors both blocking the wind, you damp motion by crashing into them. So you don't need to develop that much stability. What you really need to focus on is height growth. However, the tree grown out in the open there has no competition with other trees, so there's really no rush on height investments in stability. So it's got a much thicker trunk going on and a lot more root development underneath there to handle the higher winds that it's experiencing, because it doesn't have any neighboring trees to shelter it from the wind or help hold it up. So those open grown trees, they develop these features in response to a greater wind force. So all of these features are for resisting wind damage. They include improved root anchorage, a larger flared base, lesser shoot elongation. And when you have lesser shoot elongation, you get a shorter tree, you get shorter internodes and shorter branches. And then the tree will develop greater diameter growth, which gives them all that tapered shape. You can see it pretty clearly in this tulip tree. It has a much thicker diameter at the bottom than towards the top. You'll get thicker branch nodes where the branches connect. That's because the branches are moving all the time. They just need to be thicker to maintain their own stability. Streamlining will also happen, like with that Jeffrey pine. So entire tree shapes can change, or trees can just develop smaller leaves to help themselves streamline and evade the energy of the wind. You also get some things happening that you can't really see with the naked eye. The wood will become increased in flexibility and density, and you'll also get changes in cellular structure and division, which forms compression wood and tension wood. And now all of this is achieved just by allocating your carbon differently. Closed canopy trees put all they can into height growth because they have so much competition with other trees for light. But an open grown tree can invest that carbon in stability and things other than height growth. Okay. So this is just a picture of a formation of tension wood in accordance with a lean. But over where it says tension wood there, it's not just more wood. You can actually see the cell structure is completely different. The cells on the tension wood side, which this is actually a picture of compression wood. Anyway, it's on the right. But you can see that the two types of cells are completely different because they have different purposes. The normal cells, their one purpose is to push up leaves toward the sun, but compression wood or tension wood has a different purpose, and it is holding the tree from falling over. So completely different cell structure there. This is just a couple more examples. The one on the left is an experiment by a scientist named Taluski. He just messed with some white pine saplings here. You can see flexed 20 times per day. So it's just you with your hand just flexing the tree 20 times a day. Again, the trees on the right side of that picture are not smaller. They just allocated their carbon differently. So they have more root growth in the pots. They've got more girth on their stems. Their needles are shorter and also closer together. And the experiment on the right-hand side is on sweet gum trees. Nice illustration they did here, what they did. They staked a bunch of trees, and then they staked and shaded some trees. So they caused the trees to put all of their resources toward height development to get out of the shade, to get some light. And the trees didn't need stability because they were staked. So these staked shaded ones did not even develop the capacity to stand up on their own. So that is that's how Morphogenesis works. It's what causes a tree to develop some capacity to stand up on its own, including features that help it resist wind damage. Does anyone have any questions about thigmomorphogenesis? We good?
I think we're good still.
All right. Moving on, last section. I am going to talk about the application of some of these principles in arboriculture and forestry, and then I'm going to tell you a little bit about my research project at UCONN, where we put these principles sort of into action through forest management. Okay, so you can think about this kind of stuff when you're landscaping. You talk about putting the right trees in the right place. So some questions you might ask yourself when landscaping a house. Did you just build this house? Were there woods here before? Because if there were woods here before and you left a couple of trees, then this is a completely new wind regime for these trees. It's something that they're not used to. If you had an entirely closed canopy forest and the trees were used to having other trees to clash against, and now they don't have them anymore, they're going to need a lot of time, hopefully with not a lot of windstorms happening, to sort of develop the capacity to continue to stand. So that's one thing to think about. You can also think about streamlining tendencies of different species of trees. So you don't particularly want a tree that's going to naturally shed branches right near your house, or possibly right near power lines, or anything else you might think of. Oak trees tend to shed branches. Some of the stronger trees in general are perhaps stronger because they do this. So oaks will shed branches pretty regularly in favor of keeping the rest of the tree standing up. There's some other things you can consider about species, including the strength of the wood and the longevity. Bradford pears are an ornamental variety of pear tree that are beautiful and tend to snap in half in a stiff wind. So those are things you might want to situate in a non-windy area. If you're talking about maple trees, red maples tend to snap a little easier than like a sugar maple. They also don't live as long, so they have less potential to actually develop that sort of stability. So maybe not the world's best choice as a yard tree, but again, there are different varieties, so you have to take everything into consideration when looking at these things. Also, you want to look at the size and health characteristics of species you might have around. So I say size because despite the fact that the wind can cause a tree to be shorter than it might be if it was not exposed and in a forest, genetics is still an important part of the tree. And an oak tree is still an oak tree, and it's still going to get 70 feet tall. So you want to consider if it's right over your house or right over the power lines, or if you plant it under the power lines, even though it has no competition for light, it's still going to grow up into those lines. Also, you want to consider the susceptibility of your tree to certain diseases or insects, like boring insects, such as maples are susceptible to longhorned Asian beetles, and that could compromise the structural integrity of the tree. And if your tree is compromised and it's near your house, that's something of a danger. So yeah, all of these sort of structural things come into play when you're talking about landscaping around houses or utility wires or something. A lot of things can be considered there. All right, I'm going to stop rambling about that. We're going to talk about staking for a minute. So I don't like this picture of staking. Looks like a pretty stable way to plant a tree, but it doesn't allow for any movement. You want, when you do staking, you want the stakes to prevent the tree from falling over in a really stiff wind because it's just been planted and it doesn't have any like root capacity or anchorage yet. But you need to allow it to move or it'll never develop that capacity. You can see right here, this little tree fell over because it was so well staked, it didn't need to have any capacity to stand up on its own. Just like the experiment with the staking and the shading. If you don't give the tree the opportunity to feel the wind, it'll never learn to withstand the wind. One more thing about staking. This can happen if you leave it there for a long time, if you leave your staking materials in place. Firstly, this can girdle a tree. But if it doesn't and your tree lives, then you've introduced a serious structural defect that will compromise this tree's stability in the wind. you interrupted the grain here. So that's the long flexible fibers that allow the tree to bend and return elastically. But with this mess in there, there's no elastic here. If this tree bent, it'd break. It would not elastically be able to return to its standing position. So yeah, ways to compromise its structural integrity. All right, and we're going to talk about pruning. So obviously there's a right and a wrong way to prune a tree. We often prune to invigorate growth, so we definitely don't want to compromise the tree in any way when we do it. But if something like this happens, which I actually see a lot around southern New England, we have a lot of trees and sort of an aging utility wire system, and people love the trees, but when trees are in wires, not only do they do damage in storms, but they can start fires. Anyway, this happens occasionally. um, and it's likely that the loss of photosynthetic capacity of this tree will probably cause greater stress than the loss of damping mechanisms, the branches being all those damping mechanisms. But it's worth considering that the tree is using all of its mass, all of those branches, to dissipate wind energy. So if the tree isn't too old and this may be done over several seasons, the tree can definitely adapt to this. But it's going to be vulnerable for a while, and it's going to need time to sort of readjust to its new wind regime. Or maybe the wind regime isn't new, but the ability it has to deal with the wind is now different. It's also going to need photosynthesis again to develop carbon for its new roots or branches or whatever it feels that it needs to develop to deal with this. Also, you might want to consider, is this just going to keep happening? If you're going to keep knocking this tree back, maybe you don't want to have this tree here at all because you're constantly compromising its ability to hold itself up. Also, if this tree falls, where is it going to go? So that is another thing to consider. Definitely going to go right on that car. Okay. So we're going to talk about forest management, which is us. When we manage a forest, we can manipulate that carbon allocation that the tree is doing. So I want to talk about my study here at UCONN quick. We're looking at the biomechanics in the southern New England roadside forest. Now, the reason I could tell you all this stuff about biomechanics is that it's definitely been studied before. But primarily, tree biomechanics gets studied for coniferous trees and for plantations of trees. So it's where the real large economic losses due to wind damage happen. So in Doug fir forests out on the west, or in Europe in their big Scots pines forests or Sitka spruce forests. They're planted forests, and we gain economic value when we harvest those trees. So the wind damage can directly be calculated into dollars. However, we don't know a heck of a lot about the biomechanics of our own trees here in southern New England, or northern New England. It's the temperate northeast forest, really, these deciduous mixes. We don't really know a lot about the biomechanics of these trees. So that's why we're studying it here in New England. And specifically, we are studying it in southern New England, where we have a really dense forest cover, considering the fact that, like Connecticut, which I put maps over here of, Connecticut isn't entirely forest. It's definitely populated, but it's got a really dense forest cover for what it is. And it also has a pretty dense population of people. So we have a lot of wildland urban interface. That's where urban areas meet sort of wildland areas. In our case, all the wildland areas are forest areas. We don't have prairie here in Connecticut, but we have a 65% wildland urban interface. That's 65% of our land cover, and that's the highest of all the states, I believe. It's either us or Massachusetts, I forget. Yeah, so a lot of wildland urban interface here. And what we have is a lot of these green tunnels, which are really aesthetic. People love them. But it's a lot of utility wires in falling range of a lot of trees. And the power companies are definitely all over this. There are elaborate tree trimming regimes happening out there. However, we pose the question, is tree trimming really the best solution to this problem? So we put in 3 study sites in Connecticut in the towns of Orange and Torrington, and Storrs. Storrs is here where UConn is. So we have these 3 study sites, and we're going to see if we can use thinning, which is, the forest management technique. We're going to see if we can use thinning in these roadside sites to foster the development of wind firm features in these trees. So this is the site at Stores. This is our UCONN forest crew. We train them to use chainsaws, put safety equipment on them, and send them out there. And they actually did the thinning on our sites, which is pretty cool. So this is the Stores site. It's not actually on a road. It was our very first one, and we didn't want to start on a road. It's on a utility corridor, and the other corner is a horse pasture. So it's open on 2 sides. It's a corner forest there, and we thinned it out. So what we did in the management prescription was to select for straight, healthy trees that really had the potential to develop symmetry. So if a tree was branch heavy on one side, we would make sure the other side was cleared out so it could develop symmetrical branches on the other side and thus be more balanced. In general, we gave these remaining trees more room and more resources to develop those wind firm features that we're looking for. We also take out any compromised trees. So anything that looks diseased or is leaning towards the open areas or anything like that, this is our opportunity to take those out. And hopefully what we leave behind is a forest that can develop the capacity for wind firmness so that we can still have a forest on our roadside and sort of mitigate the threat that it poses to utility lines. This is the study site in Torrington, post-thinning. So you can see we opened the canopy right up, really allows that light resource in for the remaining trees. It also lets some wind in there. And like I mentioned before, wind will push the tree around. It induces that thigmomorphogenic reaction, so the tree can develop some wind firm features from that stimulus. So we let wind in, but we don't want to let too much wind in too suddenly. So the trees that are remaining there still have some shelter. So they still have a little damping mechanism, the remaining neighboring trees. So they're not completely exposed, but they're exposed more. So they'll start developing those features. Okay. So our objectives in this study are to investigate the dynamic properties of the southern New England roadside forest and to look at changes in the properties after a thinning treatment. So in the first year, what we wanted to do was just monitor the tree sway in these 3 sites. And then we wanted to build a model that showed us what sorts of things make the frequency of a tree what it is, and what sorts of things make the amplitude of the tree or how far the trunk displaces. We wanted to see what things go into predicting that. We looked at all sorts of parameters, stuff like the weather, the surrounding environment, the structure of the forest stand, and the architecture of the tree itself. So you can imagine for predicting sway amplitude or how far it displaces, wind is going to be a big deal in that one. Higher winds are definitely going to push the tree farther. Frequency, interestingly enough, wind is not a factor. No matter how hard the wind is blowing, it just sets the tree in motion and it starts swaying at a specific speed and it doesn't really change. Things that change the frequency are going to be things that really affect the mass of the tree. For example, the bigger tuning fork has a lower frequency than the smaller tuning fork. So if you actually change the size and the shape of the tree, then you're changing the frequency. All right, so phase 2 of this site was to thin out those study sites, and then we want to continue monitoring the sway, and we're going to look for changes in the dynamic properties. So changes in the frequency and the amplitude of sway in the years after treatment. We actually thinned the Stores forest about 4 years ago, and Orange and we're well on our way to getting some post-treatment data there. What we're looking for out of this is the extent to which the mature forest trees can adapt to their new wind regime and the time that it takes them to do that. So people have done forest thinning experiments before. You take out a bunch of trees, you leave some behind. If you thin heavily enough, you'll notice that a bunch of trees you left behind will probably fall anyway, just because they're suddenly exposed to new wind. The ones that didn't fall, they have a chance to adapt to the new wind regime. So eventually they'll stay standing, and then eventually they'll be even better at staying standing. So this is sort of a thing that foresters inherently know should work, but it's really that timing and the extent do it. Those are the things that we're looking for. We want to put some numbers behind this phenomena so that we can possibly use it to encourage people to actually do forest management in these roadside forests. So we have this one result so far. We did build a model for frequency. And this model says that it's the foliage on the tree, so whether the leaves are on or off, freezing temperatures, if it's above or below freezing, that matters, and tree slenderness, so the ratio of the diameter at the bottom to the diameter at the top. Those are the three major things that predict frequency. The wind speed or wind direction doesn't matter. The structure of the forest stand around the tree isn't really going to change how the frequency works. It's these three things that are changing the frequency of a tree, or not changing the frequency of the tree, but it's these three things that make the frequency of different trees different. Okay. So like I said, we haven't really knocked out the displacement study yet, but we do know that wind is going to be a big deal in that one. And as far as post-thinning data goes, you can definitely look at our, oh, I didn't put a link on here anywhere. So stormwise.uconn.edu is where we house all of our experiments on this sort of thing. So you can keep an eye on that. And eventually we'll have an update with some post-thinning data and really be able to see what sorts of things changed in the forest in the years after the thinning. Okay. So yeah, so we're hoping to induce the, okay. Let me go back here. Frequency is important because higher frequency is actually associated with greater resistance to wind damage. So our management should increase the stouter shapes in the trees and that frequency, which should in turn increase wind firmness. So we just have to wait for some time to really see that increase in wind firmness. All right. Yeah, that's pretty much, that's all I got for you guys today. So, does anyone have any questions about anything I said or about the study that we're doing at UConn or anything like that? Like I said, you can keep updated on it at stormwise.uconn.edu if you want to know what's going on with that study. Okay.
Thanks, Amanda. We do actually have a couple questions coming in now. So I'll
Cool.
start with the first one. How do you advise road crews to take care or to care for trees by roads after new ditching or other road work that has affected vegetation?
Ooh, yeah. So if you're doing ditching and stuff like that, you are affecting the roots of the trees, which for the purposes of biomechanics can basically be considered the branches. Um, you're taking off an integral part of its structure, the anchoring part, which is pretty important. You're sort of compromising and damaging that. So the best thing you can do is to keep an eye on those trees. You'll start seeing flagging or other signs of damage if the tree isn't able to recover from what you did. So yeah, especially if you're ditching and dealing with the root parts of the tree, it's not going to be quite as visible as the pruning messes, like this picture I have on this last slide here, but it's going to be equally compromising to the tree. So the most important thing is to keep an eye on that tree afterwards, come back at regular intervals and make sure the tree is recovering. Yeah, so that's what I would suggest there.
Okay, next one. Hayden asks, is your study broken down by species?
Is my study broken down by species? So our study covers in the three different forests. We have 41 trees, and they cover 9 species of tree. 8 of them are deciduous, and a couple of the subjects are white pines. So we do have 9 different species in this study, and I did use species as one of the potential parameters in this model. This model is just the equation on the very bottom of this slide. So we did try out species, and it didn't make a difference. So species definitely affects the type of wood that the tree puts on and its tendencies as far as like height growth goes. But once those genetic things are determined, it really doesn't affect frequency. So I cannot I would definitely not say that like oaks have higher frequencies than maples or something like that. That is just not the case. It has all to do with how the tree has developed over time and the shape that it's gotten from the experiences that it's had over its tree life. And it doesn't really have to do with species. I even looked at a breakdown of the different species and how much of a difference in frequency you can see with the loss of leaves. And that also didn't matter. I'm going to go on off a tiny tangent right here. So like I said, one of the species we looked at was white pine. So obviously they don't lose their leaves in the foliage off season. However, you still saw a significant change in their in the frequency. And we believe that it's because all the trees around those white pines lost their leaves. And since frequency is not made up of just the size and shape of the tree itself, but it has also to do with the trees that are touching it. Because if you think of the tuning forks, another tree touching your tree is just as good as another branch on your tree. So it's more tuning forks messing with the other tuning forks to come together to create a totally different frequency. So even though white pines don't lose their foliage, they're still affected by the loss of foliage from all the trees around them. So what that really says to me is that we did try and break this down by species, but that is not a good way to look at the problem. You really have to look at it as a whole forest situation, which is also another good reason that we did this study, because all of the previous studies had been done in plantations, which are just monocultures. So they couldn't really break it down by species at all. But our study sort of showed that it doesn't really, breaking it down by species is not the way to go. You have to look at it as a whole collection. The forest stand has to be looked at as a whole thing. Hope that answers your question.
Thank you. So we are being flooded with questions, so we're going to try and get to as many as we
Oh,
can. But if, as far as
okay.
participants,
We
if
got some
you,
time.
yeah, if we don't get to all of them, feel free to email Amanda after. And remember that you can type your questions into the question box in the control panel. So our next one from John is, what are some considerations with small group openings as it pertains to tree biomechanics, such as the size of openings?
Hmm. Um, so an interesting thing you might consider here, um, tree openings that are about the size of a third the height of the tree can really develop wind gusts. So as the wind travels over the surface of the forest, the thing that's pushing on the tree is these little eddies that come out of the wind that's going over the top and like dive down into the canopy a little, make these little circles down there. And that's what's pushing against the tree. As your forest is, as your forest is, it's got a bunch of little spaces in the canopy that the wind can come down, make these eddies, and push on the tree. When you start making small gaps in the forest, taking out a tree here and there, the wind has a bigger gap to come down into and form an eddy that pushes on your tree. Uh, it's at about, if you make a gap about a third the size, a size of a third the height of the tree, that's when you can, I don't want to go into the physics of the study that produced this, but that's like the maximum eddy that you can really get going. So if you make a gap that's that big, you're really putting pressure on the trees around it. If you make a gap that's bigger than that, then you've just got like your straight wind can just come in and push against the tree, which is actually not as dangerous as really creating those large eddies. It's because they circle around in there and that's the wind pulsing against the tree. So it really creates that frequency thing that can create the resonance. Yeah, so when you get a gap that's like that big, that's when you start to create a little bit of danger. So if you keep it smaller than that, you're pretty much on the safe side. And yeah, usually you're not going to clear out entirely around a tree. So even if you do create a kind of large gap on one side of a tree, the tree still has other trees on its other sides to sort of fall into. But if you're creating a large gap all the way around a tree, that's when you're sort of endangering that tree. You got to allow your trees to still connect to one another, move with each other, so that they have each other for shelter and for damping purposes. I hope that answers that question a little bit. Feel free to email me if you want further, more detailed explanation.
Okay, so a question from Dave. Does snapping occur with or against the wind more commonly?
Hmm. Um, I don't know that I read anything against about that specifically, but were I to guess, I would say that doesn't it doesn't do one or the other more commonly. It is important to note that trees move in circles when they start swaying. So they're not really moving in the direction that the wind is pushing them per se. They do start moving in the direction that they have like freedom to move into. So if there's not a tree, that's probably the direction your tree is going to start moving in. But they do move in this circular manner. So yeah, a tree is not necessarily going to fall one way or the other, pertaining to the wind direction anyway. I did put wind direction into these models that we were building, and it doesn't make a difference. It was tricky to incorporate it into the model, but the several ways that we tried it didn't suggest that it makes much of a difference. So I don't think it would make too much of a difference with the way that the tree falls. Yeah, that is that.
Thank you. Next one from Richard. Have you factored in age to your equations regarding tree ability to adapt to wind?
Mm. Um, I have not specifically looked at age in the models and stuff like that, mostly because I didn't want to core any of my trees, which would, compromise their structural integrity. But we don't, yeah, so okay, age is a big deal with the life history of a tree, and you do need to know something about age with regards to whether or not a tree can adapt to something. So if you look at a forest and you want to pick out your good trees that are going to be able to make this adaptation, you do want to pick younger trees. If you pick a small tree that's not necessarily a young tree, that means it's a tree that's been overtopped for most of its life. It probably ran out most of its ability to adapt long ago, and it's not really a good tree. So you kind of you need some experience, and you have to be a pretty good forester. And if you take down enough trees in the forest, you can count rings and kind of get a sense of what your younger trees are looking like in the forest. But yeah, you do want to consider age when you look at what trees to save in a treatment like this. Um, Reasonably sized black oaks are not something we generally saved because black oaks don't have a super long lifespan. So if they were really good looking black oaks, we're guessing they're not actually going to respond to any release that we're going to give them at this time. If they're really good looking red oaks, which tend to live a lot longer, then we did use a couple of those as subject trees. We do think that those guys will respond to this kind of treatment because they've probably got a bunch more years ahead of them. One bonus to working in southern New England, we know everything is kind of 80 to 100 years old, despite the fact that there's all these different size differences due to the different species, different modes of competition, different overtopping and stuff like that. We know everything is pretty much even aged just because of when we stopped farming around here and let forest grow back in. That advantage going for us when we make these sort of guesses. Hope that answers that question.
Okay, we have another question from Dave. Why is leaf on a relatively lower frequency in your study?
Because it increases the mass of the tree. So it's like having a bigger tuning fork. So the lower frequency means the tree is swaying slower. So with more leaves on top, it kind of takes a longer time to sort of get going almost. So yeah, we're changing the mass of the tree by adding the leaves, which is essentially making the whole apparatus bigger. And bigger things tend to have lower frequencies. Think of like a giant clock tower bell versus a jingle bell. The big one is going to have the lower frequency. So yeah. that's that.
Thank you. So we have a question from Donald. Some of the literature suggests that a height diameter ratio above 80 is a good indicator that a tree will be more prone to breakage or tip up than a tree with a lower height diameter ratio. Your thoughts on this?
Mm. So if you can see here under the tree slenderness words, I did not use a straight height to diameter ratio. What we used is dBH over height squared. So it's almost the opposite, or it gets to be the opposite. um, so I would want to look more into that specifically, the height diameter ratio of 80 or whatever you were saying there. But yeah, there are definitely specific slenderness ratios that you could say are more or less prone to falling over. Yeah, so the more slender you are, the closer your, I always, I get these confused a lot. So the closer to 1 your ratio is. Anyway, smaller dBH and greater height is always going to be a recipe for failure. Your lesser heights with greater dBHs, those are going to be the more stable trees. The exact numbers, I definitely have to write it down for you if you want further info. Okay, I'm going to stop there before I ramble on.
Question from Joanne. Can you discuss the reason that above freezing versus below freezing temperatures affect frequency so much?
Sure. So that is in a way also changing the mass of the tree. Trees have a certain capacity to sort of store liquid in them. In conifers, it's different than deciduous trees because it's like resinous. But in any case, the freezing actually will change the way that liquid is stored in the tree. So it really changes the material properties of the tree. So it'd be like having a bell made out of brass versus one made out of some other iron that you make bells out of. Um, and even though they'd be the same size, simply the different material and the different density of the molecules in the material, that's going to affect the frequency too. So it's sort of a change in mass, but on a cellular level, sort of. So yeah, that is that.
Thank you. We have two more from John. Is there value in leaving some hardwoods in high risk, wind prone red pine or white pine plantations?
Hmm. Um, is there value in that? In my opinion, this is not super science based right here, but in my opinion, there would be value simply in that you're mixing it up a little bit. The different types of frequencies in the branching of hardwoods versus the branching of coniferous trees. So we call this decurrent versus excurrent. Decurrent trees, like maple trees or oak trees that have branches kind of coming out all over the place that branch from other branches. And excurrent trees are the way conifers are shaped, and they always have like that one central leader and branches come off of that. Um, so if you were to leave the hardwoods amongst the softer woods, you're creating more mixing up of the different types of frequencies and different ways things can bang against another thing. So that would, in my opinion, the more mixing up that you have, the better defense it is against resonance with the wind. Conifers are more prone to resonance happening just because they have that central leader and it can actually get going with the same frequency of the wind. That almost never happens with the deciduous tree. So, just for the sake of mixing up the dynamics in the stand, it seems like it would be a good idea. But if you
Okay.
email me a reminder, I'll look up some literature on it.
Okay, we have
Anyway.
one more minute. One question from
Okay.
what would have been a better way to prune a tree in the picture?
What? Can you say that again?
Yeah. What would have been a better way to prune the tree in the picture?
This picture, I would have taken this tree down. Um, you can't leave branches up in wires because they'll start fires. But what you've done here is kind of create two giant pieces that are entirely capable of like getting resonance with the wind. And the center there, which now has a lot of space exposing it to the wind, is is such that all the weight is leaning outwards from the tree. Yet there has been no development of compression of no development of compression or tension wood in the middle there. So this is just a tragedy waiting to happen, I believe. Um, this tree is completely set to fail in both directions into the street and the house if a real good wind gets going. Maybe if you don't have a really good wind over a bunch of years, then maybe it can adapt. But chances are you'll get enough wind to break this tree. And most trees you can't top. So which would have been a better way to go about it, just cut it off under the lines. But that's not really possible here. You couldn't have done that without killing this tree. So I would have taken this tree out and replaced it with something that would be naturally shorter, like a dogwood or something. That's what I got.
Okay, thank you, Amanda. Thanks for that presentation.
Oh,
Uh,
thank you.
so I just wanted to share a few quick reminders before we end the webinar today. We value your feedback, so please complete the survey at the end of the webinar. You will also be receiving a follow-up email asking you to complete the survey in case you don't have time to do it this morning. Please only complete it once. We will be doing 2 webinars this month. Please join us on March 22nd for a webinar on ticks, mice, and Japanese barberry by Thomas Worthley, University of Connecticut Extension Associate Professor. Thank you again for joining us today, and we will see you next time.